Hello, thank you very much for this opportunity at the Working Memory Symposium. A lot of visual working memory studies use simple features as stimuli, such as oriented bars or colored dots. And the assumption that many of those studies make is that we have a fixed limit in visual working memory capacity. But more recent studies have found that meaningful items, such as reward objects like toilet papers or books, can effectively boost visual working memory capacity, so you can remember more information if it's meaningful. But do you also remember simple features of meaningful stuff better? Many of these studies using real-world objects often directly ask you to remember the entire items. For example, it might ask you, do you remember seeing this specific puppy? And while they found that people are very good at remembering the objects as a whole, this leaves it unclear whether the simple features of these meaningful objects are also remembered better, such as their colors. In other words, will more meaningful stimuli also boost memory of other features of the stimuli that are not meaningful themselves, like colors? And there's a reason why we suspect this. In the theory of hierarchical visual working memory, memory representation is organized as bundles of information from multiple different levels. For instance, if you see and remember this pink shape, this memorandum can be represented in two different levels, one, the shape, and the other, color pink. And in such a structure, a meaningful identity that can connect to prior knowledge, like a football, may serve as a more effective and robust scaffold for the simple features like colors to be remembered in, compared to meaningless arbitrary shapes. And if that's so, your memory of the colors should be better if you remember them onto something that is more meaningful to you. And here's our approach to test this out. First, we obtained a bunch of reward objects that are color neutral and randomly color rotated them using the color wheel that we often use. And here are some example stimuli. Then as control stimuli, we distort and morph these colored objects so that they are not recognizable anymore. And the reason why we use these distorted objects is because they preserve complex perceptual information of the real world objects, but selectively knock out the meaningfulness of them. Here, the four objects at the bottom are exactly the same as up top, just in different colors. Again, our question is, will you remember the colors better if you see them in these top objects compared to these bottom stimuli? In the first behavioral experiment, there were two conditions, meaningful condition and meaningless condition. In the meaningful condition, four of the colored reward objects were shown simultaneously for 1 second. Then there was a 1 second delay period where participants were told to remember the colors of the objects. And at the very end, they performed a two alternative force choice where one of the stimuli from before was shown in two color options. One, the target color, and the other, foil color, which was 180 degrees away from the color wheel that we used. In the meaningless condition, everything remained the same except the stimuli were now meaningless scrambled objects. And here is a quick demo of the experiment. Notice that throughout the entire experiment, we never explicitly ask participants anything about their identities. So we never ask them, do you remember seeing a jacket or a book? The only relevant feature that we ask in both conditions is, which one of these two colors do you remember seeing? We collected 30 participants' data, and here I'm plotting d prime values by the conditions. And we found that participants indeed remember the colors better when they were encoded and remembered in real-world objects compared to scrambled objects, even though identities were never explicitly asked in the task. The second experiment, we did a stronger manipulation and gave a spatial cue that indicates the location of the target color during the retrieval period. So everything else remained exactly the same, except at the very end, when people were responding, the location of the target was bolded. So in this case, participants can definitely use something like a spatial location strategy and say, hey, I remember seeing something green at the top of the screen. Therefore, I'm going to answer green. Again, I'm plotting the d prime values by conditions. And we still find that people are remembering the colors of real-world objects better than colors of scrambled objects, even though they could only use spatial location to do the task. One potential concern of these studies is that real-world objects and their scrambled counterparts are perceptually quite different. While you can still totally see the different colors in both types of stimuli, there might still be some subtle differences in people's ability to see colors. So we can address this by replacing the scrambled objects with upside-down objects, which are known to be harder to recognize, but well matched in terms of low-level features. In experiment 3, all the paradigm was identical to the experiment 1, except instead of scrambled objects, now we use upside-down objects. And we replicate the same effect. The participants are better at remembering colors that are on more recognizable objects. So far, we found the behavioral effects that more meaningful stimuli can boost simple feature memory as well. And this is true even when you're given clear spatial information to rely on. Also, this is not just due to perceptual reason, as the same effect shows with upside-down objects. And overall, these two feature dimensions, objectness and color, may interact with each other in visual working memory, mainly that meaningful identity may serve as a good memory scaffold for colors. Well, what exactly is the memory capacity mechanism behind this effect? Well, there could be two different possibilities going on here. First, when you're remembering the colors in arbitrary shapes, you may have a certain capacity limit to remember the colors. But then, when you can use meaningful identity as an effective scaffold to remember those colors, the active working memory capacity for the colors may be increased. So now you can remember the colors better. Alternatively, despite object identities not being explicitly asked, you may still use some active memory capacity to encode and remember the identity information. And if that's so, now you're sharing the active working memory capacity with the colors and identity information. In this case, because you can rely on more passive storage for meaningful object identities, now you can use less active storage to code identities for colored real-world objects. And this leads to different ratios of working memory capacity that can be dedicated towards the colors depending on the conditions, while the total capacity remains exactly the same. To investigate this, we are now using EEG to uncover the underlying neural mechanism of this memory benefit. Specifically, we're looking for an ERP component called contralateral delay activity, or CDA. For those who may not be super familiar with this component, CDA is a negative ERP over parietal occipital areas during the delay period of working memory task. This is a lateralized component, so in a typical CDA experiment, same amount of information is present on the left and right sides of the screen, while participants are cued to remember only one side. By doing so, now you can look at waveforms that are contralateral to the memory side versus ipsilateral to the memory side. And when you subtract these two waveforms, you get a sustained negativity during the delay period. And the amplitudes of this component is known to reflect the amount of capacity being used in the working memory task, as it scales with how much you are remembering. This is also known to specifically index the active capacity of visual working memory, as if you add more items, CDA will actively increase, and if you drop items, CDA will actively decrease. Similarly, if memoranda can be retrieved from long-term memory and no active storage is being used, CDA will go away. So overall, this is a very effective way of testing out how much active storage is being used during the visual working memory task. So going back to the two possibilities, if it's true that the active working memory capacity is boosted for colors on meaningful objects, we should also see an increase in the CDA amplitude in the meaningful condition. But if it's true that the working memory capacity is simply being shared at different ratios for meaningful objects and scrambled objects, then there should be no CDA amplitude difference across the conditions. The paradigm for the EEG experiment was almost identical to the behavioral experiments, except now participants are told to remember only one side of the screen. So in this case, you'd only remember the colors of the two objects on the right side. After 800 millisecond delay, participants did the same 2AFC task as previous experiments. First, we replicate the behavioral effects found before. Participants were better at remembering the colors when they were remembered in real-world objects compared to scrambled objects. But what about the EEG results? So here I'm plotting the subtracted waveform, so contralateral to the target minus ipsilateral to the target. The blue line indicates meaningful condition, while the red line indicates meaningless condition. Also, the waveforms are time-locked to the onset of the stimuli at 0 millisecond. And here is what we find. The highlighted region is the predefined time window where we calculate the CDA amplitude. And indeed, we find an increased CDA amplitude for the meaningful condition during the active working memory maintenance period. Interestingly, we can already see divergence between the two conditions early on, even during the stimuli encoding period. This might suggest that object identity already plays a role during color encoding as well. But the critical part here is that the meaningful difference between the two conditions is observed during the important memory encoding and maintenance periods. And this is not just something like a retrieval effect. To summarize the EEG experiment results, we find that the color memory benefit for real-world objects is correlated with the CDA amplitude difference between the two conditions. And this goes directly against the prediction that real-world objects should use less active memory storage, as we find larger CDA amplitude when the colors are remembered in the real-world objects. So overall, we find that more meaningful stimuli can boost simple feature memory. And CDA difference shows that this benefit is indeed due to an increased active storage. In summary, meaningful object identity may provide a good memory scaffold for colors, and this then boosts the active working memory for the colors. Thank you very much for your attention, and please also feel free to check out our preprint, which covers all the behavioral effects discussed today. Thank you.